Hello everyone! Welcome back to How Vec Works in Rust. Today, is episode 2. We left off explaining this main function. In the last episode, we explained the structure of Vec, how to construct a new empty Vec, and what happens when you push 5 items onto that Vec. That was episode 1. This is episode 2. Today, we will go over 2 major topics, pre-allocating a Vec with the with capacity method and the Vec macro. Are you excited? We begin episode 2 by creating a Vec v2 using the Vec with capacity method. We pass in 5 because we plan to push 5 elements into the Vec. The Vec with capacity method takes a usize capacity and returns a Vec. Remember to check the implementing type to identify self. As a refresher, let's speedrun the structure of Vec. Vec is a struct with 2 generic type parameters, t and a. A must implement the allocator trait and is, by default, the global allocator. Check out my first video for an explanation of this API. Vec has 2 fields, buff and len. Len is a usize and buff is a raw Vec. Raw Vec is a struct with the same 2 generics. It has 2 fields, inner and underscore marker. Underscore marker is a phantom data t. As explained in the last video, this phantom data bestows ownership of t to raw Vec. Raw Vec handles all buffer related behavior, so it's responsible for deallocating its memory at the end of its scope. Inner is a raw Vec inner a. Raw Vec inner is a struct that has 1 generic, an allocator a. It has 3 fields, pointer, cap, and alloc. Alloc is an allocator a, and cap is a cap. Remember from the last video that cap is a transparent wrapper over a usize. Moving on, cap is a cap, and pointer is a unique U8. Unique is a wrapper around a non-null mutable pointer to t that indicates that the possessor of the wrapper owns the referent. This means that the unique pointer is responsible for dropping its memory. It also means that it is the sole and unique owner of its memory, exactly as the name suggests. U8 is used here because pointer is just a location pointer. Raw Vec inner only needs to see the location of the memory, not its length. Unique contains 2 fields, pointer and underscore marker. Underscore marker is a phantom data t. We need this phantom data so that unique owns its memory and is responsible for dropping it, like how raw Vec is responsible for dropping the buffer. I'll, of course, link a blog post describing this behavior in the description. Pointer is a non-null t. Non-null is a struct with 1 field, pointer. Pointer is a const pointer to a type t. Non-null ensures that this pointer is never null. Raw Vec inner behaves as the buffer for raw Vec, solely controlling buffer allocation. It consists of the pointer to its memory, the max size, capacity, of that memory, and an allocator. Notice that it doesn't have a t generic type parameter. Raw Vec is a wrapper over raw Vec inner that parameterizes it over t. This reduces code gen because raw Vec inner doesn't need to know what t is, and buffer allocation methods don't need to compile a different version for every type. That's how Vec is structured. Vec doesn't actually deal with memory in any direct way. It outsources all of that behavior to raw Vec inner and its raw Vec wrapper. This API design is super ergonomic for users. Props to the Vec authors, as I've said many times. Lastly, here's the memory layout of Vec. It consists of a pointer to the buffer, a capacity, and a length. That was Vec. Glad we have that settled for the second time. Remember that we're looking at the Vec with capacity method that takes in a usize capacity and returns a Vec. As we saw with the Vec new method in the last video, we call an internal method, Vec with capacity in, supplying capacity and the global allocator. The Vec with capacity in method takes 2 arguments, a usize capacity and an allocator alloc. It returns a Vec. This method constructs a new Vec with its 2 fields, buff and len. Len is 0 because we're creating a vec with no elements, and buff is a raw vec created using the raw vec with capacity in method, which we give capacity and alloc. The raw vec with capacity in method takes a usize capacity and an allocator alloc. It returns a raw vec. Just as before, the method constructs a new raw vec with its two fields, inner and underscore marker. The underscore marker field is a phantom data, which we know is a zero size type, or ZST, that tells the compiler that raw vec owns its memory. The inner field is a raw vec inner created using raw vec inner with capacity in, which we give capacity, alloc, and t layout. Remember that t layout is the size and alignment of t. All sized types in Rust have a size and an alignment. The t layout associated constant is a layout containing t's size and alignment. We pass it into raw vec inner with capacity in. Remember that raw vec inner only has one generic, a. It doesn't have info about t, so we provide t's layout in the method signature. Raw vec inner with capacity in takes a usize capacity, an allocator alloc, and a layout lm layout. It returns a raw vec inner. The entire method consists of this one match statement. We match on the result of the raw vec inner try allocate in method, passing in capacity, alloc init uninitialized, alloc, and lm layout. We'll explain alloc init in a minute. Sick rhymes. First, let's look at the implementation of try allocate in to find out what it's doing. The method takes 4 arguments, a usize capacity, an alloc init, an allocator alloc, and a layout lm layout. It returns a result composed of raw vec inner and try reserve error. First, we create a variable layout using a match statement. Even though it would be equivalent, we don't use unwrap or else here because it compiles into more LLVM-IR, intermediate representation. Since vec is so fundamental, the authors ensure it is as memory efficient as possible. So we match on this layout array function, passing in capacity and lm layout. We looked at it in the last video. Let's remind ourselves what it does. The layout array function takes a usize cap and a layout lm layout. It returns a result composed of layout and try reserve error. First, we call the repeat method on lm layout with cap as an argument. This method creates a new layout. The new layout has a size of lm layout repeated cap times. The repeat method takes a reference to layout and a usize n. It returns a result composed of a tuple of layout and usize and layout error. Put simply, and ignoring nuance, repeat returns a layout where the size field is t's size times n. So the repeat method is called on our lm layout. In our case, lm layout is the layout of an i32, and cap is 5. i32's layout has both a size and alignment of 4. Repeating this 5 times, we will get a layout with a size of 20 and an alignment of 4. Next, we will use the map method to discard the unneeded underscore pad value. Remember that repeat returns a tuple of layout and usize. For our purposes, we don't need the second value in the tuple, so we ignore it using the map method. Last, we use the map error method to change a layout error to a capacity overflow error instead. So the layout array function takes a usize cap and a layout lm layout. It creates a new layout representing an array with cap elements by repeating lm layout cap times. It either returns that layout or an error. We match on the result of layout array and handle these two cases, OK layout and error underscore. If the function result was OK, we just get the layout. Otherwise, we return a capacity overflow error. Moving on, we do this if check. If the size of the layout from the layout array function is 0, we return a vec constructed using raw vec inner new in. This comment explains why we do this. When our vec is dropped, its drop implementation controls how its memory gets cleaned up. The drop implementation of raw vec doesn't perform any deallocation if capacity is 0, so we don't want to allocate any memory here. If we did, we'd be creating a possible memory leak. This way, no memory is allocated and drop performs as expected. If layout size is 0, we return a new raw vec inner without allocating using the raw vec inner new in method, passing in alloc and lm layout.align. As a reminder, this is what the method looks like. We transmute align to a pointer and construct the raw vec inner using pointer, a capacity of 0, and alloc. We went over this method in the last video too. Since you're pretty far into this video now, if you haven't seen the last one, you should watch it next. So we construct a raw vec inner without allocating memory and return it to the caller. This only happens when the layout of our planned array has a size of 0. Next, if the alloc guard function encounters an error variant, we return the error. Otherwise, we just move on. This is a very verbose way to write this functionality, but I'm sure there's a good reason behind why it's written like this. We saw the alloc guard function in the previous video. Here, we pass in layout.size. The alloc guard function takes a usize alloc size and returns a result composed of unit and try-reserve error. This function ensures that the size we will be allocating isn't more than isize max. If we're on a system smaller than 64 bits and we try to allocate more than isize max, we return an error capacity overflow. Otherwise, we return an OK. I'll link an explanation of why we need to check for this in the description. So we get the result of alloc guard. If it's an error variant, we return it. Otherwise, we do nothing. In this block, we match on init. Init is an alloc init. Alloc init is an enum with two variants, uninitialized and zeroed. Uninitialized means that the contents of the new memory are uninitialized, aka they are random data. Zeroed, which is only enabled alongside global OOM handling, means that the new memory is guaranteed to be zeroed. Alloc init represents the two allocation initialization types. The init parameter of try_allocate_in is an alloc init enum. Remember that we passed in alloc init uninitialized. We match on init and handle its two variants, uninitialized and zeroed. When we want to allocate uninitialized memory, we use alloc.allocate. When we want to allocate zeroed memory, we use alloc.allocate_zeroed. In both cases, we supply layout to the respective method. Let's remind ourselves what these methods look like. Both of these methods come from the allocator trait. The allocate method is the trait's required method, and allocate zeroed is optional. The global allocator overrides both of these methods. Both call the global alloc_impl method. Notice that the Boolean parameter is false in allocate and true in allocate zeroed. The method takes a reference to global, a layout, and a bool zeroed. It returns a result composed of a non-null pointer to a slice of U8 and alloc error. Let's run through it quickly. If layout.size is 0, we return a dangling pointer. If layout.size is not 0, we allocate our requested memory and return a pointer to that memory. Note that the zeroed bool controls whether or not the requested memory is zeroed. For a more in-depth explanation, check out my first video. So that's allocate and allocate zeroed for the global allocator. We call one of these methods depending on the variant of init. Next, we match the result of our allocation. Like layout, this is unwrap or else, so we either get the OK variant or replace the error variant with alloc error. Last, we simply create a raw vec inner using pointer, capacity, and alloc. The comment here explains the decision behind this code. As of writing this video, allocators return a non-null pointer to a slice of U8 with length that matches the requested size. So, in this case, 5. Because the length is guaranteed to be equal to the capacity, we can avoid a division here. Optimizations everywhere! Be in awe! So the raw vec inner try_allocate_in method takes in a usize capacity, an alloc init, an allocator alloc, and a layout lm layout. It creates a layout array, allocates the memory either uninitialized or zeroed, and returns a new raw vec inner. We call the raw vec inner try_allocate_in method with capacity, alloc init uninitialized, alloc, and lm layout. Matching the result, we must handle two variants, OK this and error error. First, the OK this case. We start with this unsafe block. Remember that unsafe doesn't necessarily mean that the code is dangerous. It is just that inside this block, there are dangers that the compiler can't protect you from. Inside the unsafe block, we have a comment and a function. The function hints to the compiler that the raw vec inner from try_allocate_in doesn't need to grow. According to the comment, this makes it more obvious to the compiler that calling reserve right after calling this method won't allocate. Using this information, the compiler can make optimizations. To do this, we call this function hint assert unchecked and pass in !this.needs_to_grow with 0, capacity, and lm layout. Notice the exclamation point in front of this method. The exclamation point operator operates on Boolean values, negating their value. Thus, we can infer that this method returns a Boolean. Yep, we were right. It returns a bool. Its parameters are a reference to raw vec inner, a usize len, a usize additional, and a layout lm layout. At a glance, we see that the method returns a comparison, true if additional is greater than our capacity minus len, and false otherwise. Think about it. If additional is greater than capacity minus len, then the raw vec inner's buffer would need to grow. Raw vec inner doesn't know the length of the vec, so we passed it in. Remember, we passed in 0 because we haven't added any elements yet. Basically, if additional is larger than our vacant space, our memory would need to grow. We get capacity using the raw vec inner capacity method. Notice that this method takes a parameter. We pass in lm_layout's size. The capacity method takes a reference to a raw vec inner and a usize lm size. It returns a usize. The method returns usize max if lm size is 0. Otherwise, it returns the stored capacity. This means that the capacity of a vec of ZSTs is always usize max. Since zero size types take no memory, capacity is functionally infinite, so we use usize max. I'll link some reading from the Rustonomicon on this topic. It's very confusing and technical stuff. So the capacity method gets the capacity of our raw vec inner based on the size of t. We get the capacity and subtract len using the wrapping sub method. This way, if the capacity is 0 and the len is greater than 0, the subtraction will wrap. This scenario is unlikely, but we use wrapping sub anyway to prevent a panic. We check if additional is greater than capacity minus len and return that Boolean result to the caller. This bool indicates whether the buffer needs to grow, true if it needs to, and false if it doesn't. We pass in 0, capacity, and lm_layout to this method. Capacity will always be less than or equal to capacity, so this will always return false. We invert that to true, and pass it into the hint assert unchecked function. Based on the name, we can infer that this method hints to the compiler that a condition is always true. Let's see how it does this. The function is unsafe and takes a bool cond. It returns nothing. The whole function is this single unsafe block. The safety comment explains that safety is guaranteed because the caller guarantees that cond is true. I ignored checks like this in the last video because they take too much time to explain and don't actually compile in release mode. However, I'm going to explain this one as a primer for understanding macros. So this macro, called ub_checks assert unsafe precondition, takes 3 arguments: check language ub, an error message string literal reading hint assert unchecked must never be called when the condition is false, and this line with weird syntax, cond bool equals cond rocket cond. The third argument wouldn't be valid input for a method or function, but it is allowed for a macro. Let's see how it works. Here's the definition of the assert unsafe precondition macro. Notice that it takes 3 arguments: $kind ident, $message expr, and a long complicated expression that I'll explain later. First, $kind ident means that the kind parameter is an identifier. An identifier is a name that refers to something, in this case, a function name. Second, $message expr means that the message parameter is an expression. An expression evaluates to a value, in this case, a string literal. Last but not least, let's tackle this monster. $name ident $tie equals $arg expr describes an identifier name followed by a colon, a type tie, an equal sign, and an expression. This comma and star means that we can repeat this pattern 0 or more times, separated by commas. This $parentheses comma close parentheses question mark allows for an optional trailing comma. After our list of identifiers with types that equal expressions, we have rocket followed by an expression e. This $parentheses comma close parentheses question mark again just allows for an optional trailing comma. Notice that this is the same structure. We have an identifier cond, colon, type bool, equals, expression cond, rocket, expression cond. This mirrors the structure defined in the macro. This part of the macro is called the matcher. The rest of the macro is called the transcriber. First, we define a const function precondition check. This comment explains a needed optimization due to the interplay between MIR and LLVM. During compilation, Rust is first compiled to HIR, which is compiled to MIR, which is compiled to LLVM-IR, which is compiled to machine code. The middle step, MIR, mid-level intermediate representation, can't inline this function because it would be wasted work. I'll link a blog post about MIR that might provide more insight. So we mark it as no MIR inline, and LLVM handles the inlining for us instead of MIR. The function itself is pretty simple. Its arguments are the names and types from the third parameter of the macro. It returns nothing. If the expression E from after the rocket is false, we call this function core panicking panic no unwind with our error message concatenated with the unsafe preconditions violated string literal. This will be our error message if we violate the condition, in our case, conned. So if core UB checks $kind is true, we call the precondition check function. Remember that $kind is an identifier, check language UB. Hopefully that was a satisfying enough introduction to how macros work in Rust. More information about Rust macros will, of course, be linked in the description, and we're going to talk more in depth about them later. We invoke the assert unsafe precondition macro in the assert unchecked function. Its arguments are check language UB, an error string literal, and conned bool equals conned rocket conned. Using cargo expand, we can recursively expand this macro with these arguments to see the code represented by the macro. Looks just like the internals of the macro, unsurprisingly. Notice where the arguments have been filled in: the parameter of the precondition check function, the expression in the if statement, and the error message. We won't go over how the panic no unwind function or check language UB functions work because they're very complicated, and I'm saving some of that content for another video, though the source code of these functions will be linked in the description. That's the recursive expansion of this macro. The only line of the assert unchecked function that will actually compile in release mode is this function, create intrinsics assume. We give it the conned bool. The assume function has the same signature as assert unchecked, taking a bool b and returning nothing. If b is false, the function calls this unsafe unreachable function. The unreachable function takes no parameters and returns the never type, meaning it never resolves to any value. It looks like this function invokes the unreachable macro, but it doesn't. This function is an intrinsic, so its contents are overridden by the compiler. I think one day I'll make a video going over Rust's panicking API, but that day is not today. So the unreachable function, theoretically, is never reached. We only call unreachable if b is false in the assume function. We use the assume function to assume that conned is true in the assert unchecked function. Now it should make more sense. Hint assert unchecked hints to the compiler that our newly constructed raw vec inner doesn't need to grow. This ensures that optimizations take place. After asserting to the compiler that we're done growing, we return the raw vec inner we got from the OK variant of the raw vec inner try allocate in method. For the error variant, we call this handle error function we saw in the last video. Let's review it. The function takes a try reserve error e. Its return type is never. The function will never resolve to any value. We match e.kind. Remember from the last video that try reserve error's kind has two variants, capacity overflow and alloc error. Depending on the variant of e.kind, we call one of these two functions, capacity overflow and handle alloc error. We've covered these functions in the last video. They both panic, just with different error information. So we handle our error using the handle error function, passing in error from the error variant. Finally, we've covered both variants, OK and error, of the raw vec inner try allocate in method. We've either constructed a new raw vec inner with our capacity or panicked due to an allocation error. So the with capacity in method takes a usize capacity, an allocator alloc, and a layout lm layout. It uses these parameters to allocate memory, create a new raw vec inner, and return it. We use the raw vec inner with capacity in method, passing in capacity, alloc, and t layout to construct a raw vec using the raw vec with capacity in method. This method takes a usize capacity and an allocator alloc and returns our constructed raw vec that contains our raw vec inner. We use the raw vec with capacity in method with capacity and alloc to construct a vec using the vec with capacity in method. This method takes a usize capacity and an allocator alloc and returns our constructed vec that contains our raw vec. The vec with capacity in method with capacity and global is called by the vec with capacity method. This method simply takes a usize capacity and returns a vec. All of that complexity that we just went over is completely hidden from the user. How convenient! Our main function can simply call this vec with capacity method, passing in 5, and now the v2 variable is a vec with 5 reserved memory positions. This means we can push 5 elements onto the vec without expensive reallocations. All of the memory allocation will have already happened. Letting the constructor handle allocation like this is better for performance if you know how many elements will be in the vec, because one single upfront allocation is less work than multiple dispersed allocations. Before we move on, I have a message. Like and subscribe. Okay, that's it. That's my message. Next, it's time to talk about the vec macro. This macro makes a vec out of nothing, a list of values, or a single value repeated n times. Here are the internals of the vec macro. Notice how it's defined similarly to the assert unsafe precondition macro that we looked at earlier. This macro is a little bit different though. Rather than one, there are 3 distinct macro matchers and transcribers. The first matcher is the empty case. If you invoke this macro without any arguments, it just replaces the call with the vec new, which we looked at in the last video. The next 2 are what we'll be analyzing. The second matcher is for the repeating expression approach. Notice that we have an expression lm and an expression n separated by a semicolon. According to the docs, this will create a vec populated by lm repeated n times. We'll see how this one works later. The third matcher is for creating a specific sequence of expressions. The matcher matches a list of expressions x with an optional trailing comma. This is the first matcher that we'll check out. So those are the 3 cases of the vec macro. In main, we have 2 uses of this macro. v3, a vec with 2, 3, 4, 5, and 6, and v4, a vec with 5 zeros. Let's start with v3. We expect this to create a vec populated with the elements 2, 3, 4, 5, and 6. Using cargo expand, we can recursively expand the macro, resulting in this expression. Notice that our sequence has been preserved as an array right here. We pass this array into the alloc boxed box new method. The name is so long here because it's fully qualified. We need to fully qualify dependencies in macros because when you export the macro, the calling code would have to import a dependency to use the macro if the names weren't fully qualified. To understand the box new method, you need to understand the box. Box is a struct that allocates its contents on the heap. Notice that the new method can take any t and create a box. Box is a tuple struct composed of a unique pointer to t and an allocator, by default global. Remember in my first video when I said that this exact generic is all over the standard library? Basically, even though box is a pointer to heap memory, it has ownership over its memory and will clean it up when it's dropped. Of course, the documentation will be in the description if you'd like to read more. Remember that a unique pointer is a non-null, mutable, uniquely owned pointer. So box is a unique pointer attached to an allocator. Using the allocator, it allocates its value on the heap. We construct a new box using the new method. Unfortunately for those who were excited to go deeper, this is a compiler built-in. The compiler handles the box implementation for us. Thank you, compiler. According to this fascinating blog post by Manish Goregaoker from January 2017, box is special. It is treated as a completely new kind of type by the compiler because it needs special deref behavior. I would highly suggest reading this blog post. It has so much valuable information about the history of Rust development that really brings into perspective how far Rust has come in its short but impactful life. Now we know that this is compiler built-in behavior. So the box new method takes any value t and stores it on the heap, returning the box. We box our array of 2, 3, 4, 5, and 6 using the box new method. This allocates our array on the heap. This method, intoVec, lives on a weird type. This is a turbofish. The type inside of the angle brackets is a wildcard slice. Turbofish wildcard slice lets us call a method from the wildcard slice type. There's a Stack Overflow question linked in the description that explains why we need the angle brackets. They designate the type between them as a path. The wildcard slice between them is the path type. The wildcard slice type is a slice of something. The underscore is the wildcard type, which means that the compiler will infer the actual type at compile time. Basically, the intoVec method is implemented on the slice type, but the macro doesn't know what the type will be. The compiler will figure it out for us. So we're calling the slice intoVec method. Let's see how it's defined. Interestingly, this method is parameterized over an allocator. Remember that we're passing in a boxed slice, not a slice directly. See how the type of self is a box self A? How can we pass in a boxed slice as a slice? Well, I was under the impression that there were 3 options for self in a function definition, but there seems to be more. In this case, self is a box self, so we're implementing on the slice type, but passing in a box self instead. The Rust reference has a list of all the ways you can write self. I'll, of course, link it in the description. We pass self into a function from the hack module. Must be hacky. Let's check it out. The hack into vec method takes our boxed slice B and turns it into a vec. This comment explains to us why there's no inline attribute. The function is very small and simple, so it would make sense to inline it, but inlining it caused perf regression. So now there's no inline attribute. I'll link 71204 in the description, of course. Let's get back to it. Remember, B is our boxed slice. As a reminder, don't be afraid of unsafe. It just means that we need to uphold some constraints. First, we get the len variable by calling b.len. Box t implements deref, so it can use all of t's methods. This len method is slice's len method, not boxes. Let's see how we get the len of a slice. The len method takes the slice and returns a usize. It does this by calling the pointer metadata function, passing in the slice. This function has an interesting signature. It takes a const pointer to t, pointer, and returns t as pointee metadata. If you watched my first video, you should recognize the pointee trait. This is a trait automatically implemented on all types. Some pointees have extra data attached to them. This is called metadata. Since we're working with a slice, it has usize metadata. This metadata is the slice's length. So we can infer from the function signature that we're taking our slice and getting its metadata, its length. It does this by passing in pointer to a separate function called pointer metadata. This function is a compiler intrinsic. The behavior of getting pointer metadata is different between platforms, so the compiler handles it for us. Let's decode this function signature anyway. The function takes in a const pointer to p underscore pointer and returns an m. P is a pointee with metadata m, so we take a pointee p and extract its metadata m. Isn't that cool? Rust represents the concept of getting pointer metadata with type level structure. It ensures that the behavior of this function always works as intended at compile time. Thank you, Rust. We call the pointer metadata intrinsic inside of the metadata function. We passed our slice to the metadata function in the len method implemented on slice t. We call len on our slice and bind the result to the len variable. In our case, it'll be 5. Remember, our slice has 5 elements, 2, 3, 4, 5, and 6. Next, we get a tuple b alloc from the box into raw with allocator method. We pass in our boxed slice b. The into raw with allocator method takes a box b and returns a tuple composed of the pointer to its memory and its allocator. First, we wrap b in a manually drop using the mem manually drop new method. What is manually drop? Manually drop is just a transparent wrapper around a type t. Manually drop denotes that a value won't be dropped at the end of its scope. Typically, a type's memory is cleaned up by its owner at the end of its scope. However, if we wrap a value in manually drop, it won't be dropped at the end of its scope, and the memory will leak unless manually dropped. Makes sense. Of course, the documentation of manually dropped will be linked in the description. We wrap b in a manually drop and bind it to a new variable b because we don't want to lose our box. As we discussed, this will leak memory if used incorrectly. We'll discover why this is true as we go through the method. So we first wrap our box in a manually drop. Next, we get a raw pointer to our memory. According to this comment, we get this raw pointer in a special way, without aliasing. Typically, when getting a pointer to a box, you use a reference that coerces into a raw pointer. This reference, though short-lived, has aliasing rules that could introduce undefined behavior. Terrifying! We dereference the manually drop and the box using the 2 dereference operators, the stars. We then use this &raw syntax to create a pointer without an intermediate reference. I will link a few sources in the description explaining this. It's really quite cool. It gets a raw pointer to t without creating a temporary reference. This used to be done with macros, but now it's a built-in feature. So now the pointer variable is a raw pointer to t. Next, we get the allocator by reading the box's second field. Remember that box is a tuple struct composed of a unique pointer to t and an allocator. We don't want a reference to the allocator or a clone of it, so the pointer read function gets our instance of allocator without any ownership issues. Last, we return a tuple of our pointer and our allocator. Notice that we take self by value, so after calling this method, we no longer have access to our box. Instead, we have returned its pointer and its allocator in a tuple. Typically, when dropping our box, its memory would be cleaned up. If that were the case, our pointer would now be pointing to dropped memory, and we would be at risk of reading invalid memory. That's why we wrapped our box in a manually drop. The memory didn't get dropped, and instead of box handling the memory now, we are going to handle it directly with a pointer, hence why the memory will leak if we never do anything with the pointer. So we use this method to replace our box with B and alloc, our pointer and allocator. We pass B as a mutable pointer to T, len, and alloc to the vec from raw parts in method. We know that a vec has three non-ZST fields, a pointer to its memory, a capacity, and a length. Seems like the first three arguments of the method correspond to these fields. Let's verify. The method takes a mutable pointer to T pointer, a usize length, a usize capacity, and an allocator alloc. It returns a vec. It constructs a new vec with two fields. Len is length, and buff is raw vec from raw parts in with pointer, capacity, and alloc. One more level deep. This method takes a mutable pointer to T pointer, a usize capacity, and an allocator alloc. It returns a raw vec. First, we cast pointer to a different type. The compiler infers the type because we pass it into another method. We'll see the cast type soon. We construct a cap using the cap new method, passing in our capacity. We saw this in the last video, but let's check out cap quickly. Remember that cap is simply a transparent wrapper over a usize. The new method returns a cap 0 if T is a ZST. Otherwise, it simply inserts our cap. So we make our capacity and bind it to the capacity variable. Last, we create a new raw vec with two fields, inner and underscore marker. The underscore marker field is a phantom data, as we discussed earlier. The inner field is created with the raw vec inner from raw parts in method. We pass in pointer, capacity, and alloc. This method takes a mutable pointer to a U8 pointer, a cap, and an allocator alloc. It returns a raw vec inner. Remember that we cast our pointer. In this case, we cast it from a pointer to T to a pointer to U8. This way, the memory address remains the same, which is all raw vec inner needs. Any metadata stored by our pointer to T is discarded. We construct a raw vec inner with three fields. The pointer field is constructed using unique new unchecked, passing in pointer. The cap and alloc fields are simply placed. So we create a raw vec inner from our three parts with the raw vec inner from raw parts in method, used to construct a raw vec in the raw vec from raw parts in method, used to construct a vec in the vec from raw parts in method. This constructs a vec given a pointer to our box slice, its length, and its allocator. This into vec function, which takes a boxed slice B and returns a vec, is called by slices into vec method. This method takes a boxed slice and returns a vec. It simply calls the hack module's function of the same name. It does things this way to solve an issue surrounding testing. I'll of course link the documentation describing this module in the description. We call the wildcard slice into vec method to create a vec from our boxed slice and bind the resulting vec to the name v3. That's how the vec macro makes a vec out of a sequence of expressions. Remember, this is the original macro invocation, and this is the recursive expansion of the macro. Pretty intuitive. That completes the sequence of expressions branch of the vec macro. Next, we'll see how the vec macro creates this vec with 5 zeros. Here is the macro invocation. This syntax, 0 and 5 partitioned by a semicolon, means that the first value will be repeated the second value's number of times. So in this case, we should get a vec of 0, 0, 0, 0, and 0. Let's use cargo expand to recursively expand this macro. In this case, we simply call the alloc vec from lm function with our two inputs, 0 and 5. Let's see its implementation. The function takes a tlm and a usize n. It returns a vec t, just what we're looking for. Note that t must implement clone. The function calls this method, t as spec from lm, passing in lm, n, and global. T as spec from lm means that we're letting the compiler infer which from lm method implementation to use depending on our type t. Spec from lm seems to be a trait that defines the from lm method. Let's check it out. Spec from lm is a trait with a sized trait bound, so types that implement this trait must also be sized. The trait defines one method, from lm. The method takes the implementing type self, a lem, a usize n, and an allocator alloc. It returns a vec of self. There are a few implementations of this trait, but we'll start by looking at this one. Spec from a lem is implemented for all t that implement clone. The clone bound also existed on the from lm function, so it makes sense that all clonable t have a valid implementation of this trait. You might notice something about this method that we haven't seen before. The default keyword means that this method can be specialized further. This is part of an unstable specialization feature of Rust. I'll of course link resources explaining this in the description, and I'll explain it a bit better later. For now, let's see how the fromLm method is implemented for all clonable t. We start by creating a new vec with a capacity of n using the vec with capacity in method. Lucky for us, we went over this method earlier. We know that it creates a new vec with capacity n, allocating n slots of memory using alloc. We bind this vec to the variable v. Next, we use the extend with method on v. We pass in n and a lem. We can infer from context that this method will fill our memory with n copies of a lem. The method signature hints at the same thing to us. It takes a mutable reference to our vec, a usize n, and a t value. It returns nothing. The first thing we do is call the reserve method with n. This method is intended to reserve a certain number of memory slots. Notice that we're calling this method immediately after calling vec with capacity in. Remember how we used this hint to remind the compiler that the vec doesn't need to grow, specifically to make sure that a subsequent vec reserve capacity will not allocate? Well, here we are. This reserve won't allocate and will probably be compiled out of the binary. We'll look at how it works quickly anyway, as a treat. Speed round! We call the reserve method with n. This method takes a mutable reference to a vec and a usize additional. It returns nothing. It calls the reserve method on its raw vec buff with self.len and additional. This method takes a mutable reference to a raw vec, a usize len, and a usize additional. It returns nothing. It calls the reserve method on its raw vec inner with len, additional, and t layout. This method takes a mutable reference to raw vec inner, a usize len, a usize additional, and a layout lm layout. It returns nothing. Internally, it defines a function with the same parameters as itself, called do, reserve, and handle. Notice that this is a cold calling path. This comment explains why this logic is separated into a function. It makes the function cheaper by gating all resizing and error handling behind a call that's likely to be inlined as just a comparison and a call. The rest of the method body is a simple if statement. If our raw vec inner needs to grow, remember the needs to grow method checks if additional is greater than capacity minus len. If our raw vec inner needs to grow, we call the do, reserve, and handle function. Remember that our vec is guaranteed not to have to grow at this point. In our code, we won't reach this call. What does do, reserve, and handle do? If we get an error variant from this method, we handle the error, which simply panics, as we saw in the last video. The method is the grow amortized method we also explored in the last video. I think it took around 40 minutes to explain this method, so I won't go into it in this video, especially because it won't get called in our current setup anyway. Here's the method for those who want to reminisce. Oh, memories. So we call the grow amortized method. If it returns an error, we handle the error and panic. The internal do, reserve, and handle function handles this behavior. The function is only called if the buffer needs to grow. We know that our buffer doesn't have to. So this reserve method is for raw vec inner. It's called in the raw vec reserve method, which is called in the vec reserve method. We call this method at the beginning of the extend with method. In most cases, we need this to ensure the buffer is large enough to extend. In our case, we don't need this, and it gets optimized away. Now for the rest. First, we create this pointer variable by offsetting the pointer to the beginning of our memory by len. We do this using the add method. We went over the pointer add method in the last video. Simply, it moves a pointer n slots in memory. Adding len gives us a pointer to the next free space in our vec. Next, we use this set len on drop structure that we haven't seen before. The comment says that this is a workaround for a compiler bug where the compiler misunderstands some aliasing behavior. Hopefully this is fixed soon. What is setLen on drop? What special behaviors does it have? The new method will show us. The setLen on drop new method takes a mutable reference to a usize len and returns a setLen on drop. SetLen on drop is a struct with two fields, len and local len. Len is a mutable reference to a usize, and local len is an owned usize. This comment explains its behavior. The length of the vec will be set when setLen on drop goes out of scope. This way, the compiler can tell that local len and the mutable reference len don't alias. I'll of course link the issue in the description. How does setLenOnDrop control what happens when it goes out of scope? Well, a custom drop implementation, of course. When setLenOnDrop goes out of scope, it overwrites its mutable reference len with local len. So when this struct goes out of scope, Vec's len updates. Remember that we use the new method to construct a new setLenOnDrop. We set both fields, local len and len, to the passed in len. We want the values to start off equal. After creating our setLenOnDrop with our mutable reference to our Vec's len, setLenOnDrop is bound to the local len variable. This for loop goes from 1 to n, excluding n. We don't use the current loop iteration in the inner code, so we name our counting variable underscore to denote that it is unused. This code will run n-1 times. I won't go into detail about these pointer functions because we've already seen them in previous videos, and they're very complicated. Pointer write writes a value to a memory location, and pointer add offsets a pointer by a count. I hope that's enough explanation. First, we use the pointer write function to write a clone of our value to our pointer location. Remember that pointer is pointing to the first free slot of our buffer. We write value.clone to that location. We clone value because it gets repeatedly placed into unique locations in memory, hence why t is bound by clone. Next, we use the add function to increment our pointer by 1, moving it 1 stride forward. This means that on the next loop iteration, pointer will be in the proper location to write value.clone to the next memory slot. Next, we use the setLenOnDrop increment len method to increment the internal len by 1. The method is exactly what you'd expect it to be. It increments local len by increment. This is the temporary len that will be written to our Vec when setLenOnDrop is dropped. This code runs n-1 times. It writes our buffer's memory slots, up to but not including the final slot, with value.clone. Last, we only execute this code when n is greater than 0. If n is 0, we're extending nothing, so we don't want to write value to any location. If n is greater than 0, we will write value to the final memory slot. Since we know that this is the last value we're writing, we don't have to clone it. We increment local len one more time, and, invisibly, our len is set by setLenOnDrop's drop implementation. So now we know that the extendWith method fills the buffer with n clones of value. We call the extendWith method on v with n and the lem. V is now a Vec pointing to a buffer with n clones of value. Finally, we return v. So that's the fromAlem method implemented for all clonable t. The fromAlem method comes from the spec_fromAlem trait. We call the fromAlem method, letting the compiler pick the implementation, in the fromAlem function. We called the fromAlem function with 0 and 5 to make a Vec with 5 zeros. Wait! I hear you saying, couldn't this be optimized? In the allocator trait, you showed us allocate zeroed. We could skip the extending step entirely. Well, yes! You're so smart. We could absolutely do that, and that's actually what the authors did. Diving back into the alloc Vec fromAlem method, we remember its signature. We call the spec_fromAlem trait method fromAlem, passing in lm, n, and global. We remember the spec_fromAlem method from before. Oops, silly me. I was looking at the implementation for all types that implement clone. Some types implement clone and is0. Is0. Fascinating. This is the is0 trait. It has one required method, is0. It is implemented by a great many types. In our code, we didn't specify what type of number we're working with, so the compiler defaulted to i32. We implement is0 for i32 using the impl_is0 macro. This macro takes a type t and an expression is0 and implements is0 for t. Is0 is the implementation of the method. Recursively expanding the macro using cargo expand, we get this impl block. Basically, i32 implements is0. To check if it is 0, the is0 method checks equality between x and 0. Doesn't get more simple than that, though there is some hidden complexity here behind the double equal sign. So that's the is0 trait. It denotes that a type can be represented in memory with all zeros. We can now infer why these methods must be default. This implementation is a specialization of the last implementation. In comparison to the implementation for clone, this implementation for clone and is0 is specialized. The scope of types narrowed because we added a bound. The default keyword allows the method to be overridden by specialized cases, like this one. Apparently, this is used exclusively for performance reasons, so don't be worried that you're misunderstanding an implementation detail. You're not. Okay, the from_lm method. We see that the second part of the method is identical to the implementation over clone types T. Where they differ is here. We return a different vec if our lm is 0. Our if statement checks the is0 method. Remember that this is the implementation of is0 for i32. If lm is indeed 0, we return this vec. Notice that we use raw vec with capacity zeroed in to construct vec's buff, and we pass in n and alloc. This method constructs a raw vec using raw vec inner with capacity zeroed in to construct raw vec's inner, and we pass in capacity, alloc, and t-layout, just like we did with the non-zeroed with capacity in. The raw vec inner with capacity zeroed in method takes a usize capacity, an allocator alloc, and a layout lm layout. It returns a raw vec inner. It does exactly the same thing as the non-zeroed with capacity in, but with alloc init zeroed instead of alloc init uninitialized. Remember that from a while ago? I've been writing this script for so long. We looked at the try allocate in method earlier too. Here's the method as a refresher. Now though, we use the allocate zeroed method instead of the allocate method. Since we allocate zeroed memory, we don't have to fill the vec. This is a major optimization. So we allocate our buffer with zeroed memory, using the raw vec inner try allocate in method. This is called by the raw vec inner with capacity zeroed in method, which is called inside of raw vec with capacity zeroed in. Notice that we use the raw vec with capacity zeroed in method as vec's buff and add len on our own. Think about it. It would be silly for vec to also have a method called with capacity zeroed in, because the library automatically does it for you when you use a type that implements is0. This way, the user never has to interact with this API, which is, admittedly, completely irrelevant to the core functionality of vec. Very cool and very user-friendly. This is the from_lm method implemented over all clone and is0 types T. We call this version of the from_lm method by compiler type inference. This is in the from_lm function to which we passed in 0 and 5. It's bound to variable v4. v4 will now be a vec storing 5 zeros. Now we've expanded both v4 and v3. v3 takes the sequence 2, 3, 4, 5, and 6, puts them into a slice, boxes the slice, and then turns it into a vec containing 2, 3, 4, 5, and 6, in that order. v4 takes 0 and 5 and uses the from_lm function to create a vec containing 0 repeated 5 times. Both of these variables are recursively expanded from their vec macro invocations. This is all the user has to write to create these two vecs. Recursive expansion, macro invocation. You get it. With those conquered, episode 2 can come to an end. Thank you for sticking with me through this whole thing. I thought this video would be significantly shorter than it ended up being. The perks of being thorough. As usual, leave lots of comments, looking at you, Sodiboo, nitpicking everything I said, because that's how we grow as a community. Thank you for all of the comments I've received correcting my information. I'm still a baby Rust developer, so I'm trying my best to be accurate. Also, sorry this episode took so long to release. I had a really hard time finding the motivation to work on it, but hopefully now that I've finished it, my motivation will come back. To recap, today we learned how to create a vec with a specific capacity, pre-allocating the memory so that we don't have to reallocate. Then, we learned about how the vec macro works. These concepts are all intimately linked. I hope I've been able to foster understanding that stokes new ideas into your mind. Go forth and do good with this knowledge. In the next episode, we will see how to index a vec with both single elements and slice ranges. That was How Vec Works in Rust, episode 2. Thank you for all of your support. I appreciate each and every one of you who like, comment, subscribe, and everything else. You're the greatest. I want to end this video with a call to action. Get to know your community, form bonds, find people who will fight for you and alongside you, people who will defend you and your freedoms. We are living in very scary times. Don't lose hope. Good people are all around us. Be good to each other, spread kindness and understanding, and have a happy 4 Loco Friday!